Hello, this is Jordan Veldy, and this is my Physics 1 Lab 2 projectile motion. In this lab, I will be analyzing the projectile motion of an object and creating two computational models, one considering only the force of gravity and the other considering both the force of gravity and also the drag force. For this lab, my object was a balled-up piece of paper. I used the Tracker app to analyze the video of the motion of the object and GlowScript to create the two computational models. The purpose of this lab is to determine the forces that are acting on the piece of paper during its projectile motion. The overall results from this lab showed that the two computational models produced very similar graphs, but the one accounting for the drag force more accurately represented the object's actual motion. For this lab, the system was a balled-up piece of paper. The surroundings was everything else. During this lab, we assumed that the motion of the object was in two dimensions, x and y. The object behaves as a point mass, and the object will have a constant velocity in the x direction. The procedure for this lab started with recording a video of the object being thrown over a distance, then using the Tracker app to analyze the position of the center of mass of the object frame by frame, then using an Excel spreadsheet to create a graph of the actual projectile motion of the object versus time, then using GlowScript to create two computational models of the projectile motion of the object, one with only gravity acting on it and one with gravity and the drag force acting on it, then to compare the models to determine the forces acting on the object. The physics concepts covered during this lab include Newton's second law, which states that the net force is equal to the change in momentum over change in time. We will use the position and velocity update formulas to create our computational models, and we will consider the forces of gravity near Earth's surface as well as drag. After importing my video to the Tracker app, I established an XY plane that was parallel with the table and the meter stick. I also set a calibration stick of 1 meter in the x direction that was aligned with the meter stick. Then I traced the center of mass of the object frame by frame, each frame being about 0.033 seconds. I recorded all of the data on an Excel spreadsheet, and I listed the initial conditions as seen. After plotting the data from the Tracker app, the x position versus time graph shows an upward sloping vertical line. This indicates that the velocity in the x direction is essentially constant. On the other hand, the y position versus time graph shows a parabola-shaped line. This indicates the ball is moving in a projectile motion, meaning it moved upwards, slowing down, reached its highest point, and then began moving back down with increasing velocity. I made edits to the given starter code in GlowScript to create the computational models for the motion of the object with effects from gravity and drag. I added the initial conditions for the object's position and velocity. I input the object's mass. I edited the time in delta t according to the duration of our time frames, being 0.033 seconds each. I set g equals to 9.8. I input the formulas for the position and velocity update formulas. For the first model, I set the net force equal to only the force of gravity, and for the second model, I set the net force equal to the force of gravity and the drag force. The photo on the left is the starter code, and the photo on the right is the edited code accounting for drag, with the arrows indicating where I made changes. These are the results from the computational models, the one on the left being the computational model without drag force, and the one on the right being the computational model accounting for drag force along with gravity. Analyzing the results, we can see that both graphs are very similar and display the projectile motion of the object. However, there were slight differences in the data from the second computational model that cannot easily be seen in the graph, but are very important to note. That being said, the second graph that accounted for the drag force more accurately reflects the trajectory of the object. Possible sources of error could have included throwing the object over a short distance. If we had a larger range of motion, there would have been more time for the drag force to act on the object. Another source of error could have been how much we crumbled up the paper. If we had crumbled up the paper less, there might have been a more noticeable drag force acting on the object. Do any of the models predict a terminal velocity? Neither of the models predict a terminal velocity. Terminal velocity happens when a freely falling object experiences zero net force. This means the falling object reaches a constant velocity. On a graph of velocity in the y direction versus time, it would show the line eventually flattening out, representing the velocity not changing. Looking at the graph of velocity in the y direction versus the time from this lab, it does not show this. Therefore, we cannot predict the terminal velocity. If the object were initially thrown straight up, would this change the time it takes the object to hit the ground? When using the velocity update formula and without considering drag, this can be misleading. The time it takes the object to reach the ground if it were thrown straight up would be longer. This is because when we are taking into account the drag force for projectile motion, it opposes the motion of the object in both the x and y directions for the original experiment. However, now that the drag force is only acting in one direction, it is only reducing the speed of the object in the x direction. Therefore, the object will take more time to reach its highest point and to return to the ground, and the total time will be longer than of the original experiment.